Hello everybody, I'm looking to pass on my knowledge of my hybrid jet engines that I've been working on for the last 2 years. I'm going to have some videos posted at the end, so if you want to skip right through to the end, be my guest. My goal was to make a hybrid jet engine for the radio controlled area where you could have an engine that would run off kerosene or paraffin, to smell like the original and to sound like the original using an impeller with high RPM, as well as being cheaper than your traditional turbines that you get on the market nowadays. So yeah, I'm just passing on my knowledge of what I have done over the past 2 years. It might be very handy for people like myself. I would have been very grateful to have found something like this online before I embarked on my journey. I'm going to try do it in as much detail as possible so that everybody can understand from all levels. Even those guys who have got some jet engine experience, they might even gain something from this. So for all those guys who have always wished to take on a ducted fan and have some fire coming out the back and hope that that's going to give you thrust and that would be a jet engine. It's cosmetic, it doesn't bring you any power or any thrust, but it looks great. So this is actually taking that one step further. As you can see, we're using the impellers of turbochargers with a difference. So if I take this end out and speak a bit about how the jet engine works. Obviously you can Google how jet engines work, so I'm just going to give it to you in a nutshell. But what a jet engine more or less needs is it needs a compressor, it needs a combustion chamber, something like that, and it will need a turbine. This is plastic, it's not going to work, but something with many more fins would be in the back, and you would nozzle, like that is nozzled, yeah, you would nozzle the speed of the gases into the turbine, all joined with a shaft. Where's my shaft hiding? And you would get yourself the turbine spinning the compressor. Now, to save yourself some costs, I thought I could remove the long expensive shaft with ball bearings, including the hot end, the turbine. They are usually made of quite high class metal to withstand the temperatures. So what I've done is I've removed that hot end and gone for a brushless motor to power the impeller. But you'll need to know from the start that these compressors, these impellers, they require a lot of power. Even the small little engines like this, these impellers can draw up to something like 5 horsepower in pure power to run them to their operational RPM. So you'll never easily get that from one of these small inrunners. This is a Hobby King 540. I'll give you some specs when it's put onto YouTube. And 3D printed air intake, yeah. The 3 inputs to the brushless motor, okay. And the fuel line goes in there. These extra wires you see, these were temperature sensors that also came out one of the holes. They were to measure the temperature of the motor because the cooling was a bit of a problem. What I did on this one was I had, let me take off the plastic, 3D printed plastic. You can see it's concave on both sides, concave there and concave here, so that you get some nice smooth incoming air. That's the business end. And you can see that's cogging because it's connected to a brushless motor. Normally that would just spin freely if it were a normal jet engine. Aluminium diffuser. What is a diffuser? These impellers, they spin very fast and they introduce a spiral, and if you don't straighten that spiral when it comes off the impeller, you end up with a lot of wasted energy because the wind continues into the back of the engine spiraling, and it more or less is almost a short circuit of air inside here. So what the diffuser does is, if you look carefully, you can see the scoops. The fins, they peel off the air as it comes off the impeller. Okay, and that peels it off and redirects it forcefully around the corner, straight down the back, and now they have peeled and straightened the flow from that impeller. Okay, so that's a diffuser is very necessary in order to get some efficiency going. I made this diffuser, I designed this diffuser, and had it made specifically to fit over the cooling fins. It more or less fits over that part of the other side of the motor. This is your, like I said, 540 in-runner. Specs will come on. The diffuser extends up a bit, and I used a very expensive, almost silver epoxy from America to adhere that motor to the diffuser to conduct heat through. You can even see that sensor down the bottom there is glued in place with this epoxy, silver epoxy stuff to transfer the heat. So I had a temperature sensor of the diffuser. An Arduino with the display will easily help you with that. I had one attached to there to tell me the temperature of the core of the motor. So this was, I think, this is an unmodified wheel. Let me just go back to finishing off the combustion chamber before I go into too much detail about the compressor. You will need to compress the air, you will need to burn it in combustion chambers, and you will need to have something called a flame holder. For example, that is a flame holder. Everybody who has tried to take a ducted fan and just inject gas or petrol or whatever you want in the back has probably had problems where it just blows out the flame like as if it was a candle and you blew on it. People doing that would have needed a flame holder. So the way a flame holder works is you would have a primary burning stage which would keep the flame alive. You know, after burning, if you look at an afterburner on a military jet, you will see it's got V slots where it works like this, that a little bit of air is allowed in to allow the flame to burn, and that flame is kept there because it's shadowed. There's a shadow of wind. It's shaded from the main flow of wind that would be coming past it, and that shadow allows the flame to maintain itself here, which is enough to ignite the remainder of the fuel-air mixture that would be passing by. So you would more or less have a fuel-air mixture coming through, you'd have your flame holder, and inside the center of the flame holder you would sacrifice putting in a more or less a wedge to shadow the air stream that would hold your flame for you, whilst the remainder of the fuel-air mixture would burn later on. Because of this flame holder keeping the flame in place. So you've got yourself a flame holder, you've got yourself a combustion casing. Okay, this is stainless steel. This was formed by, you take a flat plate. Have I got a flat plate? No, I don't, but imagine a round sheet of stainless steel. They put it on a former, and they force it with tools. They fight the plate when it's spinning on a lathe, and it actually takes the shape of your former, be it wood, be it metal. It gets quite hot, so they usually make stainless steel formers out of metal, and I had this made to fit my diameter of my combustion casing as I needed it. Stainless steel sheeting, you form that. You can see the spot welding is little dots all along, and that was done with a welder, a spot welder made from a microwave transformer. You can Google microwave transformer spot welders, and that'll give you a tool that will actually allow you to do quite a bit of metal work like this. This was just spot welded, and the joint is quite sufficient for this type of job. So sheet metal, microwave spot welder off YouTube will get you going. All of these parts were more or less spot welded then together, and they hold perfectly well. So we have spoken about the combustion chamber. Now you need a nozzle. This is the nozzle at the end of it. So you've got your compressor in the front, and you've got your nozzle at the back. The nozzle is very important. If that was the back of my jet engine, I would have no back pressure. The back pressure is responsible for kind of choking the flow, so that the pressure can build up inside there. If that was the back, there would be no pressure build up inside. It's more or less like if you put your hand on there, you'll feel the pressure will build up if the compressor is running at full power, and then you would let go and you would hear it like exhale. So you are choking the flow with the nozzle and at the same time accelerating the flow. So you are converting the pressure into speed. And that speed is actually what gives the jet engines their unique form of thrust over a normal ducted fan. There is no nozzle on here. It would exit at that diameter. It will not be choked down because it is not a pressure generator. It doesn't make pressure, it just makes flow rate. So we'll come more into that just now when I speak about the various impellers and propellers. So to finish off, the nozzle chokes the flow, which allows pressure to build up, which is necessary, very necessary, to burn the flame inside. If you have flames coming out of the nozzle, they are not bringing you any thrust, and it's pure cosmetic flamethrower. Yeah, it's a flamethrower. It's not a jet engine. The jet engine needs everything to burn inside before it leaves the nozzle. So if you're building one and the flames are coming out the back, it's not going to bring you any thrust at all. So you need to build up pressure to get that fuel that you need burnt inside, and that's the key to trying with these low pressure fans and having a nozzle. You would need, with a fan like this, if you wanted to get any thrust, you would need such a long combustion chamber in order to burn the fuel at the speed that comes out at. So a lot of these, this diffuser, for example, converts the speed which is coming off the tip of that, which is near supersonic, coming off the tip of that impeller, slows that right down to the greater diameter before it gets sent back for burning. This guy, on the other hand, he just speeds up the flow and he continues with that speed throughout. So you'd have to have this huge diffuser combustion chamber, very long, where you would burn your fuel inside and then come back down. And you can already see from that impractical size that you would have such a you would have a fuselage as a combustion chamber for your little ducted fan, and that is why you don't see these flying, because they just don't bring you that thrust to weight efficiency. The other thing I wanted to finish off on is, for example, that flame holder. You can see these slits in the side. They are strategically placed so that you allow a cooling film of air on the periphery. So the outer ring of air, as it flows through, needs to remain unburnt. If you have the flame burning throughout that whole mixture, you will end up melting off the nozzle. Yeah. So you need to design your combustion chamber such that there is a periphery of unburnt air which runs along the outside and then more or less forms a skin of cold air or unburnt air before it comes out. That's the only way you're going to stop your nozzles from melting off. So that's what I wanted to explain about the combustion chambers. Let's go into the fan, the differences in the fans. This is, like I said, off a turbocharger. It's a 50 millimeter fan. There'll be some specs on the screen to give you all the details about that. This is unmodified. It's a standard fan, and what it does is it leaves the bottom of that plate is flat. Yeah, it comes in and goes flat, so the air leaves straight out on this one. That is for maximum efficiency. That is what turbochargers will be running at in your car, and your turbines and your little model jet engines, they'll all be like that. This is a diagonal fan. Notice that there is an angle here. Okay, there is an angle here. It's not coming out at 90 degrees like this one. It's coming out diagonally. Okay, let me get a good angle for you there. You can also see on the tip, I had this machined down. I'm looking for my screwdriver. You can see the tips. It was about out to here, and I had that machined inwards, and you can see the angle of that as I spin it. You can see it's clearly angled, which means that the air which flows in is then exited in a diagonal fashion, not in a 90-degree fashion. So it doesn't do this, it comes out at almost 45 degrees. This actually reduces the size of the diffuser. You'll notice that this diffuser is a lot more snug. Again, I don't want to measure it, but you'll see that even though that impeller is bigger, the diffuser is smaller. Okay, so let's explain why that is and why I chose that. This will achieve minimum volume, maximum pressure. This will achieve medium volume, medium pressure. This will achieve maximum volume, no pressure. Okay, so those are your three types of fans. You could call this propeller. Okay, propellers work off low RPM, even though those guys spin like no tomorrow. Consider it a low RPM when you talk about these guys. This guy, and you'll see on the screen, I'll give you a compressor bubble. Each turbocharger has a bubble chart where it shows you where it works in its best efficiency. And the efficiency is up in this one, probably around the 140, 150,000 RPM area. Now that is a lot more than these little guys with their 40,000 or 30,000 RPM that they spin at. Okay, if you spin this guy 30,000 RPM, he's going to laugh at you because there is nothing down there. Okay, and that was the first problem. That is the first learning curve to you guys, is they need to scream with RPM before you will get any efficiency out of them. So why did I go diagonal fan? Well, the diagonal fan is more or less a compromise between the ducted fan and the centrifugal fan. The diagonal fan is a compromise in such that I'm not going to the same, I don't need the same RPM to achieve an efficiency. So my bubble of my graph, which doesn't exist because this is more or less machined to my size, but you will notice, I'll give you the specs for comparison, it's a much bigger inlet and it's the same diameter outlet as that one. So it's still doing the centrifugal bit, you still get some pressure, but it is a lot more propeller-like or ducted fan-like. Okay. Again, the straighteners, you don't need much to straighten the flow because it's not coming off at the same angle. So that showing you how that is cogging and the angle. comes off a bit more shallow. That is sufficient to straighten the flow. It does spiral a bit still, but spiraling is nice for some fuel air mixture later on. This I designed myself, drew it up, had it made in China, cost me a cool $500 to make, which is why I'm passing on this this knowledge to yourselves of don't waste too much money on redoing what I've done, or at least do it better. I had this designed to more or less take my 3 brushless motor wires forwards. There you can see them from the brushless motor. This was a Chinese manufacturer of brushless motor who gave me the highest RPM spinning 4-pole in-runner. It's again about the same size as the 540. I was able to clock it very high because I actually designed the diffuser as its casing. The whole casing is actually, if I took that off, you would see it's an in-runner, and the stator is actually pushed up snug against the inside of this, which means it's a perfect heat sink. The diffuser is obviously air cooled. It doesn't get better than that. To cool the motor itself, so I could overclock the motor, and I was able to achieve about 1.5 kilowatts of input power into this. Probably, I don't know, half of that only coming out, but you could get it quite hot. And with a cup I'll show you later, I had a way to heat sink the magnet as well. So yes, that was the expensive diagonal fan that I had made, and performed pretty well, although again the thrust to weight ratio was not sufficient for flight. Let me speak now about, so that's the 3 different fans that we spoke about now, and we can combustion chamber. The types of combustion. Now, I spent a lot of time burning the fuel in different ways, and that is something I also need to pass on to you. I had 5 different types of combustion. One of them was with a fuel injector. If you take your, if you have heating at your home and you use a diesel or a kerosene type oil burner, you'll notice that they have something like this in the bottom. It'll take the kerosene, it'll preheat it, it'll then inject it through one of these guys, and you'll get a very nice flame. And you'll probably have a fan assisting that to get you the combustion gases to leave your cooling fins. So this is a standard kerosene or diesel injector. It comes off the boilers, so you can get those more or less from any boiler shop. And the reason I was allowed to use this, whereas other jet engines don't, is because they've got that shaft. Normally there'd be a nice shaft in the center of this that would be in your way, going to the turbine at the back. So I don't have that problem, so I can have a nice center burner using an injector. The injector will not work off your basic fuel pump. It needs a lot more pressure, around 6 bars, to give you a nice fine mist spray that comes off the injector. It's quite a slow moving mist, but there's a lot of it. And this one faces forwards, and as you can see, that's the shadow. Yeah, that's a tin can. That is the shadow, so the air would be rushing past. If I just put that on there, the air would be rushing past. This is a heat shield for the ducted fan, for the brushless motor. So that's a heat shield, and your air would come through, it would hit that and say, I can't go down there. I had some tiny holes that I was testing to help breathing, but they weren't necessary. So the air goes past this and makes a cavity for the flame to hold. That cavity is sufficient to have a stable flame. The rest of the air comes in here, circulates with the fuel, and makes your fuel air. So you'd have a core of burning straight here. Again, little slits in the periphery to allow some unburnt air to keep your your casing from getting too hot. Okay, this is another long casing, stainless steel, which was used with this type of combustion chamber. So that's injectors. Did that work well? It worked well, but you've got the negative part that you have to have a fuel pump, quite a powerful fuel pump. I modified it. I used a little brushless motor outrunner to do the gear drive, the gear pump, and yeah, it was bursting the seams if it ran up. So it was a good one. You could probably have even a smaller one than that, sufficiently to do your 6 bars. Remember, it doesn't need much fuel, it just needs high pressure fuel. So do I want a speed controller? Do I want that with my fuel? Well, yeah, that's where the negative side of the injector comes from, is the high pressure fuel pump. Okay. I wanted to run my project of liquid fuel and not gas fuel, so i.e. no propane tanks or anything like that. I find them a bit too volatile. So we have that. We have then a wick. What I did with this, think of it as a candle wick. It's a sponge. It's made from steel wool. The steel wool you use for polishing your pots and pans. And what I did is, this is a 2-in-1. This is a form of fuel injection as well as a flame holder. So you can see the tiny holes in the back. They allowed some air to seep through into the wool. That made it actually quite an effective burner. Because of the shape and the tiny holes, a lot of the wind just obviously passed right past this, again causing that shadow, and that held the flame very well at high speed and burned sufficient fuel, and would be my recommendation to you if you're ever trying to mess around with this, to start with this. I held, so you carefully twist the wire wool, the steel wool, you carefully twist it into a type of string, and you hold it down there and you do your weaving. This is stainless steel wire. You get that from the fishing line, and you just unbraid it. You get one of those with many little braids, a very fine one, and you can more or less carefully weave it around and sew on that steel wool, because it gets hot, onto your tin to keep that in there. You would then use a form of vaporizer tube. Okay, this is a copper tube, and you would think that the copper would melt, but actually, because the fuel is coming in and it's a liquid fuel, it took a lot of the heat to get that fuel to a burning temperature, a boiling temperature, which meant that this tube, even though it's full on in the flames, it doesn't melt, it doesn't even glow very much. And what happens is you embed the end of that tube into the steel wool, a couple holes drilled, like if you look at this one, a couple holes drilled in the periphery where it would terminate before you crimp it, and that would then leak the boiling fuel into your steel wool, and that would be a perfect burner. This is like a 2-stage or double burner, where the copper coil went inside the base and then came out, went into the upper one before it terminated and got crimped. So you had like a double barrel. From there, the air would actually come in, have to go around the second one before it continued, just giving you an extra layer of burning. And it worked pretty well. I would say that is a good way to start. It's lightweight, requires a minimal fuel pump of low pressure, small little guy, just to get the fuel in there, because remember, we're running our engines with a lot lower pressure than most of the engines, the actual real gas turbines. Tried all different sizes, that's copper again. Tried all different sizes and ended up realizing that even just the small ones are sufficient to get you what you need, be it brass, be it stainless steel tubing, anything, as long as it's as the wall thickness is not too much. So we then move on to the cup burner. Now this guy, who cost me a lot of money, there was another ball bearing in there which allowed that to actually go inside. It would sit all the way up to here. Okay, something like would sit all the way up to there. Okay, now notice the outside is tapered. It's diagonal, well, diagonal-ish. And the way a cup burner works, if you Google a cup burner, it'll give you a lot more detail. But in a nutshell, if you inject fuel, this is spinning very high RPM. Okay, spinning very high RPM. If you inject fuel into the back area and you allow it to touch the back, it will be flung to the outside. So it'll run along on the inside though, it'll fling to the outside, and it will run along the inside of here. Because it's tapered, it'll move forwards by itself, but at the same time it will be getting much thinner. So you have this micron thick fuel that is reaching this opening, and you can imagine then as it's spinning you're going to have a sheet of paper thin fuel being expelled from that. So that thin fuel is then torn to pieces with wind that blows past it. So you can imagine if that burner cup is spinning and expelling fuel out here, you will have the air rushing past these fins, and they will just tear that fuel film apart. And actually that's how these very large cup burners work. They're quite effective. My problem is that it spun so fast and there wasn't enough height on those fins to actually allow time for the fuel to go with the flow of the airflow. So I ended up flooding the inside periphery of the combustion chamber, which meant my fuel air mixture was not efficient. You would then have a flame holder behind that to take the fuel air mixture and allow it to burn in the area just behind here. Okay, so that's a cup burner that would be spinning, and fuel would be coming out here and mixing. So that's one way of a trial and error that I did. That was not very effective. The other one is pulverizing. That worked pretty well. If you imagine a hollow shaft, and you take a fuel and you stick the fuel, okay, that doesn't fit inside, but imagine your tube would fit inside that hole. Now if that shaft is spinning and you inject fuel into there, then this would be loose fitting. Okay, this would be loose fitting. It would have play so that the fuel could go in and get out. Okay, but because the fuel is spinning, you get the same type of cup effect that it wants to spray out. And as the fuel sprays out, I had pedals. I don't have it with me, but imagine like pedals that the fuel would come up, this would be spinning, and it would literally slap the fuel droplets at high speed with a lot of energy and splashing them. Just like as if you would take a hand and you would splash a bucket of water, it just splashes it and pulverizes it. Now we're talking 20, 30, 40,000 RPM, and that pulverized the fuel. I had the same problem. This was the combustion chamber I used, one of my most effective combustion chambers. Came out of a thermos flask cup, very thin stainless steel. And that guy, that was the back end of the motor. So the back end of the motor, you can see there, it's actually got a hole drilled in it. Had the pulverizer on it, and it would pulverize the fuel inside the combustion chamber area. And you would have the fuel splashing around here on the inside. Obviously air mixing in these tiny holes and through these holes allowed it to burn, and because it splashed onto the hot combustion chamber and not splashed into the periphery of the casing that isn't that hot in this area, as you can see by the temperature marks. This guy obviously is discolored all the way up to the front. He gets hot, and the fuel instantly evaporated in here and gave me a very good combustion before it left my nozzle. So yeah, that worked very well. The last one I tried, that still needed a fuel pump to get the fuel to the shaft. The last one I tried, if we show you this one here, and we put our nozzle back on, our air intake back on, if we click him on, you will see that if you know anything about Venturis, that there is a suction happening here. This is a low pressure area, and a lot of pulse jets use this. They have, if you imagine, there's my fuel coming along, and if you just leave your fuel here without the pump, so we're just taking a fuel line here and you leave it there, and as that spins and sucks air, it's going to cause a vacuum and suck fuel by itself. You don't need a fuel pump for this. And what I did then is I had a variable plate, which was like a little washer. You can see that if I show you that again close up, that's flat. Okay, that's flat on purpose, and that allowed a stainless steel exit fuel tubing to again come there close to that and allow on the inlet side fuel to be sucked in. Okay, so fuel was sucked in, and the problem this one had was that the impeller itself, so the fuel happily went in, and the impeller itself pulverized the fuel like we spoke of before, but pulverized it and accelerated it so fast that again it actually stuck to the upper part of the diffuser that would have gone in that way. So I found that all my fuel was flooding in this area because it got accelerated so fast that it just had that weight. It couldn't take the corner like the air could. Even though the droplets were small, they just couldn't take that corner, and they ended up flooding the perimeter of the engine. So although something was burning, it was very inefficient and unsuccessful. So that was the 5 types of combustion chambers or fuel injection systems I tried, and I have to say the best one was this type, which I would recommend if you need if you're going to try something like this. So let's move on to a nozzle. I explained to you why you needed to choke the nozzle, and how do you know what size that should be. So what I did is I had a nozzle which was tapered, and then I had a tapered nozzle insert, and if you can imagine, as that moves inwards, the cross-sectional area increases. So you can see it increases and decreases. So what I did was I had these engines running on their thrust stand, and you can't just take your finger whilst that's running and just shove this in, because you're going to have forces against you here, so you're going to get incorrect readings. So I had this mounted on the thrust stand as well, and I had a sailing servo turn this threaded shaft threaded inside here as well. So obviously you can imagine this just moves forwards and backwards those 2 centimeters, which is sufficient enough to give you a huge change of probably 100% change in area of the exit nozzle. So when it's running, and one of my videos coming up will show you the nozzle actually going in and out to show me different thrusts. So my thrust scale would vary depending on how much the cross-sectional area was, and that way I knew, because I was messing around with so many different diffusers, impellers, fuel injectors and everything. I had to each time figure out more or less a manual way to get the nozzle size. You can calculate it, but it was a hell of a lot easier just to flick a button and find the sweet spot to get the right size. And once you know the sweet spot for that configuration, you can have the right nozzle cut, which people would say that's quite a small nozzle, but it's because of that pressure that it actually made quite a high speed. It required that small nozzle to get that sweet spot, and that is about the nozzle adjuster. So I think that's about it, and we'll go on to the videos now. Thank you. Well, thanks for watching. To summarize the running and all that, the problem with pressure is the RPM of the impeller, and we just can't get the RPM that high that those impellers really help us out. If you use a ducted fan, which doesn't need that high RPM, you're going to need a much longer, heavier combustion chamber. So again, the weight does not pay off. If you took that same motor with the same batteries and you had a reduction gearbox spinning a half decent propeller, you'd probably be up in the 3 kilograms of thrust. So, you know, it's not going to be a thrust machine. This is a good test to show you someone who's taken it seriously to try and make a hybrid jet engine. There might be, I have seen some others out there which had some success, but again, they were either slightly cosmetic or they were giving false readings of their actual thrust output. So subscribe if you want to see more crazy stuff like this. I've got a couple more things to show so that I know who of you are interested in this. Thanks for watching. Bye for now.